Sometimes it works.
PowerPoint and
yeah, I think the problem was just that I changed the display. So those of you who are doing check-in and check-out, or reading the check-in messages, will have seen that there was quite a bit of activity with the so-called test field module. And because I was so much involved in this, I want to tell you a little bit about why this was such an important thing, and it still is a very important thing. The test field module actually started with the SVN revision number 4200, and now we have 10,000. So it actually started halfway through regarding revisions, but that really corresponds, it corresponds to the year 2004, 2005. So it is approximately halfway into our pencil code time. But it really only was in the last few years that this whole thing took off. So here is the scientific output so far using the test field method. It started with one early paper in 2005, and then there was quiescence, and then it really started with a bunch of papers all of 2008 here. So it started off with the paper actually with Shaurya Shur. When he came, he is from some place in India, but working with Kanaswami Subramania at Pune University, and he was visiting us at Nodida, and they were asking whether it is really true, whether the kinematic alpha effect and the kinematic diffusivity are strongly dependent on the magnetic Reynolds number, as they are in particular flows, like, for example, the so-called Galloway-Proctor flow. But we wanted to answer this question for isotopic homogeneous turbulence, and that's what we did. And the most exact method, or most accurate method for doing this is by using the test field method, which I will explain in a moment. The other, so this is for isotropic turbulence, kinematic alpha effect in isotropic turbulence simulations. We also had a paper with Petri, who is here, where we calculated the magnetic diffusivity magnetic diffusivity tensor. So these are not necessarily always isotropic objects, they could be tensors, and that's also what we can calculate with this method, in the case where we have rotation and we have shear turbulence. So it's, of course, rotation introduces anisotropy into the turbulence, and shear also does the same thing. And then we had another paper where I forgot to include any transparencies into this talk here, the so-called scale dependence of the diffusion and also the alpha tensors. If you look at diffusion properties of a large-scale signal, the amount of diffusion may actually depend on the wave number of that signal that you have. And that's what is meant by scale dependence. And that really corresponds to saying, so in other words, if you take the diffusivity at a certain wave number, then you have a corresponding viscosity or diffusion coefficient that depends on the wave number. And it's in limited cases when the turbulence is small enough of scale that this doesn't really matter. But once the scales of the turbulence become comparable to the scale of the signal that you are looking at or that you want to diffuse, then it becomes important.
So does the diffusivity fall normally?
It falls, yes. Normally it falls. For turbulence it falls.
Because the larger scales are just large scale erection and are not really diffusing. The larger scales, they're just kind of...
No, I would simply say it becomes less efficient if the two scales become comparable. And it behaves in wave number space like a Lorentzian. That means 1 over 1 plus k squared. Or k divided by kf squared. So yes, and then we did the same thing for accretion disk turbulence. That's in this paper included. And then we, for the first time, did the same thing for the nonlinear case. That's in this paper. So these last three papers are still in submitted modus, but they're all on the archive here. And so this one is the same thing as basically the Shaurya Shur paper, but then now for the nonlinear case. This is a case here where Druba, Mitra, and Petri Kepler and Lisa Tabakol have been collaborating with me, and this is where we look at the alpha effect density visibility. So in that sense, like this, but in the presence of shear. So then there's also anisotropy. And then finally, another paper which actually is not using the test field method as such, but it uses the test field module, because the equation is very similar to the induction equation, and we wanted really to use the induction equation in parallel to the rest of the MHD equations, and that's done in the paper here with Silkner myself. So why do we look at alpha effects and turbulent diffusion? The reason is really that in many situations in astrophysics we know that large-scale magnetic fields can be generated. We want to understand why this is the case. In astrophysics, of course, we know the Sun has a large-scale magnetic field, galaxies have a large-scale magnetic field, and we need to pin down at some point or the other what are the precise mechanisms that actually do accomplish this. But examples of large-scale field generation in numerical simulations are manifold. Here's one of just helical turbulence. Everything completely isotropic. There's no shear or no rotation. Just helical turbulence. Helical turbulence is isotropic and homogeneous. People often say, if it's helical, how can it then be isotropic? Yeah, that's really because helicity does not violate isotropy. Helicity, you should think of a box of screws. So each screw is right-handed, right? In that sense, the whole system is right-handed. But if the box of screws is mixed, you shake it, then all the screws are completely randomly oriented. So all directions are represented. And yet it's fully helical, or could be fully helical.
Oh, what? Sorry?
Screws. A screw.
Oh, okay.
Or spirals or something. You take lots of spirals in a box, so they all point in different directions, but they all have the same handedness. That's what this is, of course, about, and other people in biology would call it, of course, chirality. But that's not really, there's no direct connection with magnetic fields here, we think. So what you see here is that what is shown is cross-sections of a component of the magnetic field at the periphery of one side of the box. And you see it at different times. During the early phases, when the magnetic field is still growing, it's randomly oriented, and only at later times the magnetic field builds up a really large-scale structure here. Another example here is a simulation from Petri, where there is also shear flow present. In that case, time is shown along this axis, and one spatial coordinate is shown in this direction. And that's the direction which is perpendicular to the plane of the shear flow. So what you see is both the x component and the y component both are, this is the streamwise component, this is the cross-stream component. In both cases you see, after some time, the buildup of a large-scale magnetic field. Large scale means if you average the field, averaging is indicated by an overbar, you get something which is finite and of significant amplitude. And in this case, there is a finite amplitude magnetic field, and it also shows long-term spatial and temporal order. Spatial order because if you look at this as a function of space, you see a sinusoidal modulation. If it as a function of time, you also see a sinusoidal modulation. So it's large-scale spatial temporal order. And this, of course, is basically what is going on in the Sun, for perhaps similar reasons. We don't know yet. Another example of large-scale magnetic field generation are these following two examples, which are different in the sense that in those cases here the turbulence was driven by a random body force in the momentum equation. And that's something which is really artificial. There's hardly any force in nature which really acts as a full body force. The closest we could have is if you have supernova explosions in the galaxy. That could act as a body force to a reasonable approximation. But otherwise, that's really not the case. And instead, the source of instability is not an explicit driving, but it is an intrinsic instability in the fluid. And there are two types of intrinsic instabilities. One is the convective instability, and the other one is the magnetorotational instability. The convective instability you have if you have heating from below, and you exceed a certain critical radial number, you find convection, and so this system here, it's again a simulation by Petri, is showing convective turbulence throughout this entire time. And at a certain, during this time, magnetic field is exponentially growing until it eventually reaches equipartition. That means that the magnetic energy becomes comparable to the kinetic energy. And when this happens, in this case where he has sufficiently strong shear, in other cases where there's also such shear that would not happen. So what happens in the presence of shear is that he actually generates also a large-scale magnetic field with a certain spatial modulation, and in this case a temporal order which is constant in time.
In this setup, in this run, you have no shear until 400, and then...
No, there's shear all the time.
All the time?
All the time, yes. And what we see is that the prominent large-scale magnetic field only shows up in the saturated state. And that's very typical. We had the same thing in all the other cases so far. So far, we don't know really of large-scale magnetic field generation in the kinematic regime. But that's all.
Yeah, sure. But in that case, it's so average.
It's exponentially growing, so you just don't see the.
You also don't see it very much, yeah.
Field.
Yeah.
Yes, so it's so average. Then, okay.
You're wondering whether there is maybe a large-scale field, but you don't see it because it's so weak. Is that what you're saying?
Yes, but what he's saying is you have to know. I agree that you have no large-scale field knowing linear growing, but and then just in one time, boom, you get the large-scale field.
Mm-hmm.
But that's the same case in the second plot on the right.
Right. It's the same.
Yes.
Yeah, here the large-scale is growing progressively.
I would have almost had another plot which would show the ratio between the average component, which is the large-scale component, and the total field. And Petri may not have done so. So that those typically reach something like 50%. These ratios after those times, and they're typically on the order of 7% at early times. And 7% is also what you would expect if you have a certain finite number of eddies in a simulation. Then you would get a random number, plus and minus. You will always get a finite average, just because you have, if you roll the dice 5 times, for example, you will never hit exactly the average. You will always have a Gaussian distribution around the average. Okay, and that Gaussian distribution has a certain width, and that's what generates these 5% or 7% in the early stage. So with magnetic nonlinear unity, we don't know of any example of a large-scale magnetic field in the kinematic regime. But in the nonlinear regime, we do have successful dynamo action in many cases. So these are then, and that's finally the example of the magnetic rotational instability. A number of you are interested in, especially Anders here. And there we have, again, spatial order, in the sense that there's a large-scale magnetic field here. Here it actually looks at certain times a bit anti-symmetric, but not quite. Here it's more symmetric again, with respect to the top and the bottom of the domain.
What is the boundary condition?
In this case, it's a potential field condition.
So we do with periodic boundaries. It is occurs even with periodic boundary conditions.
Yes, that is of course rather remarkable.
So one question. So
Yeah.
you see these large-scale field structures function of Z. But if you want to average over, say, in the other direction, and take it from the Y and from the X, would you see zero power? Or would some of the power on the Z-dependent mode somehow spill over to some modes that depend on X and Y also?
So you ask whether there's a dependence on X and Y?
Yes, just even if it's 10 times smaller. But I'm asking, is it a million times smaller or is it 10 times smaller?
I mean, it's never that much smaller. It's normally 10% smaller. I mean, 10 times smaller. That's basically related to what I just said earlier, that if you have completely random conditions, you have 7% of the ratio of mean to average field, mean to total field. And if you have in a large-scale dynamo successful and fully saturated, then you have 50 to 70%.
Well, I'm not talking about random field, I'm talking about ordered field, but not only Z-dependent, but maybe X-dependent.
Yeah.
So
I mean, you yourself told me that you actually found some evidence for such.
yeah, but I'm just wondering if just the fact you have a very a strong large scale set dependent field, if just some nonlinear interactions there would mean that it spills over and creates a little bit of power on X dependent modes also.
I mean, you would, if you have an interesting story to tell, then it would be one where it would not just be the spilling over, but there would be a real mode in X and X direction. And that's certainly a possibility. It's certainly a possibility. So if you find this, that's great, and it should be understood and modeled further. And the bigger the domain is in the horizontal direction, the higher chance you will have to find that. And once you find such a thing, one can and should look at such things again with the test field method, which I will mention in a moment. At the moment, I make a pre-selection. I basically ignore then by averaging over the X direction. I will ignore the X dependence and also the Y dependence. The Y dependence could be interesting. These are phenomena that in the sun are called active longitudes, for example. And some people see such things in rapidly rotating convection simulations. So, in other words, if you do a real simulation and you find structure in any direction, you should of course not choose averages that eliminate such a structure. So the averages should not be something magical, and you should not be looking what happened before you average. You should first look what happens, and then you will see some structure, and then you do the average, and the average makes the structure only more pronounced. And then you ask yourself the question, if given that there is such a large-scale structure, is there a way of understanding the origin of a large-scale structure in terms of a simpler theory? So if you have a structure which is really just depending on the z direction and on time, you may wonder whether there is a simple, reduced theory which only depends on z and t. One of the things, of course, I should remind you of. Based on the original equations, such a thing can never work because a dynamo requires 3 dimensions. There's no dynamo which works in 2 or even 1 dimension or 0. So dynamos require 3 dimensions. There's no way of simplifying this. And if so, it would only be a description of what happened at large scales. And that's called metric theory. Yes, I thought of slipping in this one picture here because we have heard a little bit about turbulence simulations, about spectra. And that's how a compensated power spectrum looks like. Niels, of course, has been looking at compensated power spectra throughout most of his years around 2004. He has had 8 papers, all of which have compensated power spectra, I think, in one way or the other, most of them. And so this is the typical case of a magnetic Prandtl number of unity. A compensated power spectrum means, power spectrum means you are doing a Fourier transform, you are averaging over shells in wave number, and look just at the radial dependence in wave number space, and that's what's plotted here. If you have a Kolmogorov spectrum, the power would fall off like k to the minus 5/3. If you compensate by k to the plus 5/3, so that the result is flat. And so here you see that it's reasonably flat. And by having a normalization with respect also to the total dissipation by some factor, the whole result becomes non-dimensional, and this value gives you the so-called Kolmogorov constant, which is a little bit bigger than unity typically. But this is now for helical turbulence. That has not been done before. And this is Prandtl number 1 at 512 cubed resolution. What you see first of all is this is the injection scale of energy at this wave number 4. You see then a Kolmogorov cascade to the right, and then there is being energy dissipation at approximately this wave number. So that means all the energy is going down to smaller and smaller scales, and then it's being dissipated. But there's a small amount of energy which does not go to the right, but it goes to the left, and that's all the stuff that has to do with the knottedness of magnetic field. It's the fact that magnetic field is helical. And magnetic fields have the property of this knottedness being a conserved quantity. And so you cannot bring it to smaller and smaller scales, and your knots would be tighter and tighter, and that really is impossible. So the only way that they can go is to expand, to relax. That's how a knot can behave. So the only way for a knot to relax is to go to larger scale, and that's what happens here. So you hear the dark line is the magnetic energy, whereas the dashed line is the kinetic energy. Kinetic energy, of course, will go down because there's no supply of energy anymore, there's no inverse cascade of kinetic energy, so no kinetic energy at large scales, but in the magnetic energy, because of this conserved quality, being magnetic helicity, there is magnetic energy at large scales, and this is in the final saturated state. And now the interesting question is what happens at smaller and smaller Prandtl numbers. Of course, what you also have been looking at back then is this work which is papered together with Chekhov-Zhihin and Niels. These are lines of constant magnetic Prandtl number. If you go to smaller and smaller, this is for unit Prandtl number here. This is a Prandtl number of 0.1, and this would be 0.01, the diagonal lines. Then the critical magnetic resonance number that you need to reach before the dynamo becomes excited becomes bigger and bigger and bigger, making it eventually impossible to get your dynamo working.
Does the dynamo get equally excited? I mean, getting excited is just material to dynamo action, but is it always the same amount of dynamo action even at lower Prandtl numbers?
No. It becomes really less efficient. But one thing I should emphasize, this is for the so-called small-scale dynamo, a non-helical dynamo.
Yeah, I'm just saying this is relevant for the discussion, which Toby also knows for,
yes,
for sense and risk about resolution effect.
Yes, and so all these simulations are non-stratified. Toby, right? When Toby did such things, they're non-stratified, then there's no source of helicity. The only way you get helicity is if you have stratification.
Yeah, but there is an effect in passive resistance and MRI is that if you increase the resolution, your turbulent activity decreases. And it's not clear what's causing that, or is it Toby?
Turbulent activity goes down.
About this.
Yes.
Because there is a Prandtl number dependence, but it's not clear that the Prandtl number would change at higher resolution, right? Or is it the same?
No, that is, I don't think that's known.
So the only thing I can see is that the magnetic resonance number increases, and then somehow the turbulent activity decreases.
Well, I mean, there are two issues. I mean, one is the resolution dependence, one is the Prandtl number dependence.
Yes.
And it's not clear how they...
No.
So both are important, of course, but the Prandtl number dependence simply has to do with the following. This is a very small sketch, because some of you may know this already. If you have an energy spectrum like this,
small-scale dynamo.
yeah. So the small-scale dynamo is it's called a small-scale dynamo because it generates magnetic fields preferentially at small scales, both at the kinematic but also in the non-linear stage. And the wave number at which the magnetic energy peaks is the resistive wave number, and this becomes, of course, equal to the kinetic wave number dissipation, which the Prandtl number is 1. But if the Prandtl number becomes less than 1, that happens, the magnetic energy is being dissipated at smaller and smaller wave numbers. And that means that the peak of the magnetic energy, the wave number where the dynamo really operates, is more and more inside the inertial range. And the reason why it becomes harder here is because you are now going out of the diffusive range where everything is really smooth. The velocity increments scale linearly with the separation. But here they scale sublinearly, they scale only with the 1/3 power. And so that means if you take velocity differences, divide them by the separation, those become singular, like lengths to the minus 2/3 power. And so then, in that sense, the turbulence is called rough. And in this case, here there is this thing which is not even plotted here, there's this so-called bottleneck effect, and that's even more rough. And that's why it becomes first harder. And our latest simulations by Iskakov show that perhaps after this the curve goes down again and becomes constant.
Your prediction that it go down for right?
That's Iskakov result, yes, or indication that it becomes constant again. It goes a little bit down, and that's actually from this plot here. So there's a bit of a mess, but it showed it only so small.
So after
But it goes down here, it's good.
If it was to go down again, that would mean that if you want to excite a very low Prandtl number, you wouldn't need as high a magnetic resonance number.
Yeah, then eventually the magnetic resonance number would always be the same, yes. And that would be on the order of, let's say, 300, 400. And that becomes still very expensive. If you have a magnetic Prandtl number of, for example, magnetic Prandtl number of 100, and you have a fluid Reynolds number of 300, that means you have 30,000 for the fluid Reynolds number. The magnetic Reynolds number is 300. Now, a completely different story if it's helical, and of course astrophysical turbulence is more helical than non-helical typically. And then nothing of this is anymore true. So having spent so many minutes in answering these questions, that's all, for most parts of astrophysics, perhaps irrelevant, because that's really what happens in astrophysics, where you have small magnetic problems and you have helical turbulence. And so what happens if you have helical turbulence? You see here the magnetic energy cuts off earlier, and it cuts earlier still at 0.01, and the dynamo is still excited. The large scale magnetic field is unchanged at all these times, and it goes even down to a Prandtl number of 100, of a thousandth. And the dynamo is still excited. It's just that this cuts off very early. Now, another thing which is really remarkable here is, in order to reach such states, here we have a fluid Reynolds of 600 or something like this. Here, if it was 600, I would find that most of the energy is being dissipated magnetically, and here even more so. And so because so much energy is being dissipated magnetically, I can actually drive the flow harder and harder, because the dissipation happens along a channel of dissipation which is happening at large scales, small wavenumbers. And so therefore I can actually force the turbulence harder and harder. So here I was able to reach a fluid Reynolds number of 1,100, here of 2,000 to 300, and here of 5,400.
You force the turbulence by the magnetic...
No, I force it kinetically. I force it kinetically at this wave number. So that's extremely unexpected, of course.
But your inertial range doesn't expand.
The inertial range does not expand, no, because the laterally goes down.
And that's because all the energy is dissipated magnetically.
Prematurely, yes. Yeah.
That's basically because you are estimating your Reynolds number by Kf.
Yeah, based on the large scale KF thing, yes. Where here's still a lot of energy, yes.
Maybe if you use scalar microscale, things will change.
Yes. Now the thing that really matters, it is actually the fluid, the magnetic Reynolds number. It matters for dynamo action at large scales. So the critical condition for dynamo action at large scales is simply that the magnetic Reynolds number must be bigger than 1. Or 1 modified by some scale separation thing. So it could be between 1 and 2. And so here the fluid Reynolds number is 5. The magnetic Reynolds number is 5. So big enough, just about. So I could not go perhaps to 10⁻⁴. But so astrophysics perhaps will really not have any problem with small magnetic Prandtl numbers. The other thing that happens is, in those cases when the magnetic Prandtl number is small, during the kinematic stage, large-scale dynamo action is perhaps already possible to see, and not just only at the nonlinear stage. So I thought this was interesting to show you, because those people, if you were remembering that there is a problem of magnetic Prandtl numbers, then really that's not a problem for helical turbulence. And also the fact that if you have small magnetic Prandtl numbers, you can dissipate most of the energy along a pretty safe channel at large scales with the magnetic field. Right, now we will come to the test field method. But before that, a little advertisement that there's a big grant that was awarded to us, and we will be hiring lots of students and postdocs and assistant professor and long-term visitors. So it's an ERC grant. So now, test field method. So what we are really interested in is an equation here. This is the induction equation, but it's an induction equation with overbars, which indicates that we are only talking about averages. And so therefore these averages may now only be dependent on time, and perhaps one spatial coordinate, or perhaps the second one. In this case, only one spatial coordinate. If you average the equation, you will have a correlation between the velocity. Here we have the mean velocity and the mean magnetic field, but you will also have a correlation from the small scale velocity field indicated by lowercase letter and the small scale magnetic field indicated by lowercase b. And this is, of course, the critical term that makes this theory very different from the corresponding direct original equation. in the original equations just have a U cross B term, they don't have such an electromotive force from any small scales. Now the question is, how does this expression look like? And the general ansatz that we can try to verify is one where it does depend linearly on the mean current density, J bar, but also on the mean magnetic field. And based on symmetry arguments, you can say, this quantity here is like the electric field. It's not quite the electric field, but it's like an electric field. Electric field is a polar vector. Like the velocity is a polar vector. If you change the coordinate system z into minus z, then the corresponding velocity would change its direction. So these are called polar vectors, whereas vectors like the vorticity and magnetic field belongs also to this class. They are axial vectors. And they do not change their direction after such a symmetry change. And so if you have such vectors connected by some tensor, or if you take only that diagonal component as a scalar, then the corresponding scalar in between must be a so-called pseudoscalar, and that pseudoscalar would change sign if you change the sign of your coordinate system, or the orientation of your coordinate system from left to right, for example. Therefore, this is a quantity that can really only be existent under non-trivial conditions, if you have a violation of parity in general. One example, of course, is if you have helical turbulence. Then indeed this is violated and this tensor can be present. And indeed it will typically be present. This tensor is an ordinary tensor because both J and E are polar vectors, and so this is just an ordinary tensor. And this is called the turbulent diffusion because its diagonal component just looks like the ordinary molecular diffusion. But this tensor will have components that are enhanced. It may also have off-diagonal components, and with the method I described here, we can determine all of these components quite accurately. It has been tried in the past using various attempts. One is the so-called correlation method, by which you actually use the actual turbulence simulation as it's going on. You measure all these quantities, and you try to determine these unknowns. And the number of unknowns that we have is 4 plus 4. The reason is that this vector has only two components that are non-trivial. In the z component, these must all be 0. That's because of the divergence of b is 0 in the z direction. Also the divergence of j is 0 in the z direction. Therefore jz must be 0. So there's 2 times 2 components here, 2 times 2 components in here. So this has been attempted in the past. These methods are not very accurate, and now with the test field method we can determine very accurate such tensor components. This was first explored by Schwinner in his PhD thesis since 2005. And so then after he presented this and talking to Karl-Heinz Redler, we implemented this method and have been producing lots of science results. Let me then explain how this method works. The original induction equation looks like this. And when the average, I explained it already, you replace everything by an overbar, but by replacing this by an overbar, you will pick up the correlations from the small scale magnetic fields, which is the critical term that we want to calculate. But in order to calculate this, we must know how big these correlations are. And so now we can write an equation, evolution equation for exactly these small scale magnetic fields. We do this by taking this equation minus that equation. We subtract the two equations and we obtain an equation for the fluctuations. And it has 4 terms plus a diffusion term. One is large scale B times large scale U times small scale B, and the other way around. And then we have small scale minus the average subtracted, because we subtract these two equations. So that's the equation, and it's different from the original induction equation, like this one, for example, because first of all there is an inhomogeneity. This is an inhomogeneous term. So inhomogeneous means that if the small scale magnetic field were to vanish, then this would vanish, 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 but this one would not vanish. So this would be an explicit driver in this equation. And therefore this equation should not be confused with the induction equation. So test field equation is not really the same as the induction equation. Furthermore, we subtract out the mean electromotive force. That means that in this equation there can be no production of a mean magnetic field at any time. So that's the equation that we're interested in, and now we put a bar here between these two calculations, because now we want to simply investigate the properties of these equations rather than solving for a particular system. And so that we do then by replacing now this mean magnetic field by what we then call the test field. So then we can replace this B by something which is now given. And it can be a constant field, for example. In some boring cases, it can be a sinusoidal field. And it can be a sinusoidal field pointing in any of the spatial directions that are relevant. By putting in the field in different directions, we have a class, different classes of such fields. We enumerate them by letters P and Q. So we have a B11, B12, 21, and 22. And for each of those opposed fields, we obtain corresponding fluctuation equations, and we solve those. We take orthogonal sets of test fields. 1 would be one where there's a cosine dependence in the x component. 2 is one where we have a sinusoidal dependence in the x direction, and then likewise for the y direction, cosine and sine. So altogether 4 different test fields, but they are all vectors, so we have altogether 4 times 2 equations, because there's 2 relevant vector components. So we have altogether 8 equations, and we have also 8 unknowns. And so we can determine at every time step and every z value all the unknowns. And the unknowns are of course, these tensor components, but let's take an example where we calculate, where we take, for example, the Bernoulli field. And if you take the 1,1 field, we get an electromotive force which is called also superscript 1,1. It's this one. So we have then cosine times the 1,1 component of alpha. The derivative of a cosine gives us sine, and therefore we have this in between here is now a rank 3 tensor, but there is related to the rank 2 tensor like this one, but it's of course an obvious correspondence, but this is more straightforward. So we have now, in this case, we have one additional vector equation with 2 unknowns. So in order to, but only one component is relevant here in this case, namely this one x component. So now we have another equation by using this test field instead. So again, we're talking about alpha 1,1. Now this one, of course, is on the sine, therefore we have a sine. If we take a derivative of this, j comma k, we have a cosine. So now we have 2 different equations, and now we have our 2 unknowns, one alpha 1,1 and eta 1,1,3, which is related to eta 1,2.
So this test field is evolved
It's
separately
constant.
from
No, it's a constant. This is time independent.
You evaluate the right-hand side of this last induction equation, but that does not in any sense influence the magnetic field in the calculation.
It does not influence the actual magnetic field that may influence the velocity field. Yes, it does not. In fact, what the input to this equation is really the velocity field u, both the fluctuating components in 3 places, plus its mean component is finite. So it's really a method which analyzes any velocity field. It doesn't actually care about the actual magnetic field, if it's there. It only cares about the actual magnetic field through its effect on the velocity field. So that was this. We know now how to do it, and we have the same matrix. And these, of course, are just simple rotation matrices to invert. This is here's a rotation matrix already, and the inverse of this is the rotation matrix with a sign, with a minus sign, being swapped from here to there. And we have the same matrices for the other remaining components. Now we have all the components. So we can then validate this, of course, for cases where we know the result. So we know the alpha effect for certain flows, like, for example, the so-called Roberts flow. That's a very simple flow field which consists of cosine x and sine y dependencies here. So this one is a fully helical flow, maximally helical, and it has positive helicity.
positivity?
Has positive helicity, yes, this flow. You can change it, of course, by putting in a minus sign, and it has negative helicity, it's maximal again. That's a very simple flow because it's just two-dimensional. By the way, this when I was talking earlier about three dimensions being important for dynamos, that does not mean that the flow has to depend on all three directions. It's the magnetic field which has to depend on all three directions. So obviously the flow in this case only depends on x and y, and it's therefore two-dimensional, even though it has a third component. But the magnetic field must have, in addition to an x and y dependence, must also have a z dependence, and it will have a z dependence, otherwise there will be no dynamo. Okay, so now we can calculate our fluctuations, and based on this we can calculate the mean electromotive force and calculate that for alpha ij and beta ij. That was what we have done, and the alpha effect in some normalization depends on the magnetic Reynolds number in this particular fashion. The dots are the lines that are computed, the values that are computed analytically, and the line is corresponds to an analytic formula which has been semi-numerically obtained. There's one common approximation that is done in many of such calculations, which is called the second-order correlation approximation. So if you do analytic theory, you can only solve this equation linearly, up to linear terms, but these two terms are nonlinear terms. So in the simplest approximation, they are simply neglected. It's called second-order correlation approximation or fourth-order smoothing approximation. If you do that, we can also do it numerically, we can neglect it, and can therefore reproduce what some simplified analytic results would get. Then the alpha effect would increase with Reynolds number exactly linearly. But this really becomes wrong, of course, at a magnetic Reynolds number slightly below unity. Not too surprising.
So basically it becomes wrong as soon as the dynamo sets in.
Yes. Yeah, yes. No, but let's see. That is, you can still, that approximation, you can still get away with this. There's two ways of getting out of this. The first is if you take a box which is very elongated in the z direction. Because then the Reynolds number that really counts is the Reynolds number based on the large scales. No, I think that's not right. No, it's correct. It really becomes, it's this one. Yes, so that's right. So therefore, there's no such result, at least not for the Roberts flow, where you can have a successful dynamo, and this Soka approximation still being valid. That's correct then, I think.
Maybe I missed that, but these plots on the right-hand side, they show the parameter as a function of the forcing, as a function of
on the right-hand side?
Yeah.
They depend. They actually show what I thought I neglected to show, which I did certainly neglect to show for turbulence. Actually have it here, the wave number dependence. So remember I told you about the Lorentzian wave number dependence? That's here the case for the Roberts flow. Here I happen to have these plots. You can even have negative diffusion for small.
You can have negative diffusion at small k.
Yes.
So that's the negative turbulence.
Yeah, but you have still a molecular diffusion, and the sum of the two is still constant. There's a number of other examples where this can still be even large, so negative diffusion often can happen, and yet, in none of those cases is there a dynamo that is driven by the negative diffusion. Because then, for example, some other effect, the alpha effect, becomes bigger. And the reason is that this goes with the wave number k squared. Diffusion enters with wave number squared. So a small case, the k squared is very, very small, and the alpha effect goes linearly and enters the equation linearly in k.
But what I mean, I thought the alpha effect would also create a large scale diffusion.
Yes.
Both the negative diffusion would create a large scale diffusion.
Yes.
The alpha effect would
Exactly, and this one becomes completely subdominant, even though that already could produce something.
But I guess
because this is
my question now is that the negative diffusion would create large scale dynamo at all scales. It doesn't matter if z dependent, x dependent, y dependent.
Yeah, but no, all scales not, because here exactly I tell you how the scale dependence look like. It could not do it at large scales.
So
that's simply because it's...
I guess what I mean is that you were shown earlier some dynamos that created predominantly on z-dependent scales.
Yes.
Because of the alpha effect.
Yes.
But here you have a negative turbulent resistivity, and maybe this is one thing that might actually create even at large x-dependent.
Yeah, but only for very small wave numbers, at very large scales.
Yeah.
And then you can ask the question, how important is this effect relative, for example, to this alpha effect here? And as I said, this either you have to multiply by k squared. and then becomes extremely subdominant. And you still have, of course, a molecular diffusion, which you have to take into account. And these results even should depend on the value of the molecular diffusion. And therefore, this typically is, if anything, more important in all the cases that I've found negative diffusion so far. I was once very enthusiastic, wow, we found some negative diffusion just even maybe 1 month ago or something, and it turned out it's not really interesting. Yeah, right. Now the other case. So what was the Roberts flow? Is a stationary dynamo. We know stationary flows are produced, for those people who know this, they are called slow dynamos, so they cannot produce dynamo action in the limit of large magnetic resonance numbers. Turbulence, however, and this is here in our turbulence, I didn't write the word turbulence anywhere, and this is now a three-dimensional isotropic helical turbulence. It's different. It can produce large, also fast dynamo action. And so here is now shown the alpha dependence, eta dependence for this flow. So there is no analytic theory available anymore, and this can only be done numerically, and it was only done since this year, for the first time that we actually know this. And what we find is, again, for small magnetic resonance numbers, it increases linearly with the magnetic resonance number, and then it becomes constant. Now, what is the value of this constant? It's the value is, it turns out to be close to a quantity alpha naught, or likewise with the turbulent diffusivity, close to eta t naught. And this quantity is given by these very simple expressions, which we may have seen in the literature, and they are typically regarded as pretty rough approximations. So alpha is equal to minus 1/3 times correlation time, which you can estimate by the RMS velocity and the wave by the forcing scale, and the kineticalicity, or for the turbulent diffusion, the RMS velocity squared. Now, these approximations, which we regard as something rather rough, turn out to be accurate to high accuracy. So this value is unity, meaning that this approximation is accurate within error bars, up to Reynolds numbers of 200. So that was extremely unexpected. But this is really for isotropic three-dimensional turbulence. Now, a few other cases. What happens in the case absence of helicity, non-helical flows, but if you do have rotation, then we do have an off-diagonal component to the turbulent diffusion tensor, which you can split off by determining the off-diagonal component. It turns out to be that the off-diagonal component is antisymmetric, and then an antisymmetric off-diagonal component you can express by a vector. Epsilon ijk is the vector, of course. Epsilon ijk times delta is your matrix, which is the antisymmetric matrix. And it turns out that this delta increases now first with increasing rotation rate. For small rotation rate, the so-called Fourier's number is small, or 0, becomes 0 then this result. It also increases with magnetic resonance number, and is finite. But then after that, maybe it goes down again. We haven't done very large values yet. Another even more interesting case is the case of shear turbulence, and there it has been argued you can have dynamo action on its own. And that is if you have an off-diagonal component, in particular the eta 2-1 component, if it has the right sign. So you can determine now the dispersion relation based on this electromotive force, and the dispersion relation, which means the growth rate, it turns out to be either purely real or purely imaginary, is given by this expression here. There's a -1, this is normalized in terms of diffusion, turbulent diffusion, but then there could be a term under the square root. If this term is positive, the square root would be real. Otherwise it would be imaginary, it's uninteresting again. And so obviously we can only have a successful dynamo action if eta 2-1 has the same sign as the sign of shear. For numerical reasons we always have negative shear because the parallelization has still not been corrected for the case of positive shear. So everybody has done doing negative shear. We corrected this?
I think you're using the Fourier which that works for
Oh, you have done try negative SN, yeah? Positive SN.
And that works, okay.
What was the computer?
Oh, the parallelization, of course, you have to calculate which processor you are having. you have to communicate with. And that depends on rounding. I mean, so you have to calculate an integer. You calculate integers by taking an int function. And if a quantity is negative, you have to add or subtract 1. So that means you have to think hard. Do you have to add or subtract? And of course, I always did it for negative, and then I thought once very hard, and I did it correctly, and I checked, and it was not working, and then I fixed it, and it was working. Or maybe it was you actually who did it, right? But Niels did it, of course. Niels implemented the chain box, of course. And but I mean, he never used it actually. So, but then for the other sign, we always knew you have to think hard again. And then somebody asked me, does it work? And I told them, yeah, you have to think hard. And nobody has done it so far, except now we do it with
It would be much more convenient if the shear varies in the y direction, wouldn't it? So there would be shearing periodic in y rather than x.
Why is that better? Because some other people do it like
then
it.
you have to, these things, you won't have to shear across, you won't have to interpolate along y, which means you wouldn't have to interpolate along across processes, but rather along x.
Correct.
Everything would be trivial.
Yes, that's right, yes.
And that's what fluid dynamicists do.
Yeah.
They always have.
Yes, exactly. Just that in astrophysics has never been done.
Yeah.
So we need to wait for somebody who has the time to do it, and then it would be great if it's being checked in.
Also, we have to redefine the shearing sheet form.
Yeah.
That's probably the same as having said y, x. But the French do that always. The French tend to have the shearing sheet when the other way around. With y pointing in and x pointing.
Yeah. Anyway,
Take a little bit on.
so we are now having a negative s, and we are looking for a negative eta to 1. Do we have a negative 1? So we look at this, we find eta to 1 is shown here. Here's the turbulent diffusion, by the way. It's again unity in normalized coordinates. It makes the shear stronger. It increases, if anything. It's not being quenched. Also surprising. The Reynolds number increases linearly, and then it becomes approximately constant like before, but it also is a bit bigger than 1. But this eta to 1 component, which we may hope should be negative, is positive. It's an error bar, certainly. And also here. And so far we
Was
have
this
not
the
found
term
that.
that's responsible for the, was this the term responsible for the
Yes, it's a 2-1 component. So based on this particular method, if there is a large-scale magnetic field generation, it could not be due to the shear current effect because the sign is simply wrong. And here are then the simulations that Petri did, and there are actually similar pictures by Geoffroy Lesueur, which I regard as looking very similar. And so I interpret his simulation as being due to a similar mechanism, which in this case cannot be this shear current effect. It must be another
You mean
mechanism.
the MRI simulation?
Yeah, yes. Would you not agree they're looking similar?
Which paper are you talking about? Open
Yeah, I think, yes, exactly. Yeah.
So that is non-stratified.
Yes. And this is also not
There is
sure.
some kind of large-scale dynamo.
Yes, exactly. Yes, exactly. Very much the same thing. So there's no velocity, and otherwise everything is the same. The only difference is there's also rotation.
Could that also be the incoherent alpha?
Yeah, of course, exactly. That's what I'm saying. But so that's our proposal. There is fluctuations. Alpha is 0, but it's only 0 within a Gaussian envelope. So there are fluctuations around it with plus and minus. And below the level of fluctuation, it increases somewhat bit with whatever this quantity is to be, which is, I think, the magnetic rounds on that. And so, yes, these fluctuations could be responsible in those cases. That's the proposal that goes back to a paper with Vishniak already in '97 in connection with accretion disks. We applied it to accretion disks actually back then. But now we are applying it to everything else. In particular, Proctor also applies it to also the solar dynamo. Okay, so finally, what happens if you do it? This was all for the kinematic case. If you're looking now at the nonlinear case, what do we have to do? We test the test field method, and it cares about the velocity field, which comes from this equation. It does not care about the magnetic field, except through the Lorentz force. So, as I said, the test field is not the magnetic field. It should not be confused with the magnetic field. There would be, and has to be, in the separate equation, the actual magnetic induction equation, here in the uncurved form as usual. And its Lorentz force would modify the magnetic velocity field, which then would show up in the test field equation and would then show up as modification of the alpha and eta tensors. Everything else is the same. So here are the results. Based on general arguments, you would expect that now, because there is a preferred direction given by the direction of the magnetic field, the alpha and eta tensors are no longer isotropic. And people often think isotropy is really complicated, and let's forget about this. I will show you in one slide or so that it will be actually very important. So what typically happens is that alpha 1 and eta alpha 2 come in with opposite signs. So that's one major way of quenching the dynamo, by having this one trying to quench this one. But you have, of course, something which is non-isotropic, and in isotropic tensor, they're trying to quench each other.
I think to ask you, what is different now from what you've shown before?
Oh, it's now non-linear. Now we do non-linear. So the magnetic field enters in the system, and therefore we have no longer isotropy. We lost isotropy.
So before you didn't have the Lorentz force?
No.
Okay.
Completely kinematic. So before I ignored this equation, just took the continuity equation and the velocity equation.
And why you stop on the next slide?
Here?
Where do you find this expression for alpha? Why you choose this?
Okay. If the magnetic field is the only vector that provides an anisotropy, then you now can start construct tensors which have the valid symmetry properties. And of course, that's one such construct. There would be, however, in principle, the following few constructs as well. You could have a construct in terms of the current density, Ji, Jj. You can certainly have that. And in general, you will have this. In this particular case, you don't have it because we are doing here shearing. We are doing here a non-shearing simulation with just Beltramic flow. Isotopic homogeneous fields, and that produces magnetic fields that are of Beltramic form. And that means J and B are aligned at every given point. The magnetic field at the large scale is fully helical. So if J is therefore parallel to B, then even though you may have such additional components, they would still show up as in the same form. But if this is violated, it will be violated in the presence of shear, but then there will be additional anisotropies. Also in the absence of boundaries, or in the presence of boundaries, there will be additional components. This and mixed ones as well.
Maybe you said that already, but in the kinematic case, in the shearing, in the presence of shear, do you also assume the alpha tensor to be isotropic?
In
the linear case, in the presence of shear.
Then alpha is non-isotropic. So for example, then
how do you decompose alpha in that case?
then there are
we just look at 4 components.
yeah, either you just don't care about it, you just determine numerically what it is. It's getting more complicated. But we have it, by the way, in our paper, which came out in March.
Let's say that when you have shear, then there are again 2 unit vectors which are directing isotropy.
Right.
One along the direction of shear and one along the direction of the velocity. And here you're using just one unit vector in this construct. So they are using the 2 unit vectors. You can again construct the possible tensor, and then that will appear 4 scalars. You see what I mean? And then that basically you decompose alpha in that way. But that doesn't help because the tensor itself has 4 elements, and if you decompose it that way, you again have 4 elements.
But this is basically a truncated, well, there could be more terms with higher powers in B.
But they would.
Assumptions.
But it would then look still like ijk, and then it would be b bar squared. So again, it would not show up as a new element because it's still proportional to the bi unit vector, bj unit vector.
So that would mean that alpha 2 can depend on B.
Yeah. Both, by the way.
Okay.
Yeah, both are, by the way, B dependent.
Okay.
Yeah, forgot to emphasize this. So in the beginning we were not really quite sure. That by beginning I mean by this like in April. I think by April we were still quite unsure whether this method is actually really correct. Karl-Heinz was saying, yes, of course it's correct. Kando was saying, maybe not so sure, and I was saying, I only trust and I have the simulation giving consistent results. And so we really were not completely convinced. And certainly everybody else outside our collaboration, which is the one with myself, Karl-Heinz Rader, Matthias Reinhardt, and Kandaswamy Subramanian, everybody else from other places were rather unconvinced about anything so far. And so the paper is not even accepted yet. Except it would be accepted if it's not a letter. So, now, one consistency check is to say, if you have a saturated dynamo, we can linearize, and then believe you should get a growth rate which is 0. So if you project now, apply these tensors along the direction of the actual magnetic field, which is the same as these ones, of course, then the alpha, then the dispersion relation consists simply of the sum of the two alphas times k, and the sum of the two etas plus the molecular one times k squared. And this should all be 0. And it does become 0 to very high accuracy, or to good enough accuracy, in the case when the dynamo is indeed saturated. One other thing of warning here, so if you calculate, so that happens to us in the beginning and was then pointed out by Matthias, if you actually determine this, you run your simulation and you average over the z direction. Yes?
This consistency check can be done also in the linear case, right?
Yeah, of course. And but then you don't have then you have only a 0 in the marginal case. Here you have it in for all random numbers. Once you have
you can have alpha 1 Q1 minus theta 1 Q1 squared for 0.
Yeah, or something finite if the dynamo is growing, of course.
Yeah.
And that works out.
But in the linear case, the dynamo will always keep on growing.
Is that always up?
The linear case, the dynamo will always keep on growing.
It
But
will
that's
always.
a marginal.
Yes, of course.
Yeah, so that's the test here. And yeah, the warning was this: if you think we always everything was always z independent so far, so this one we calculate because there's only noise in the z direction, we just average it out. Now in this one, this of course is 0 in the linear case. In the nonlinear case, it's actually finite, and the turbulence is now not only anisotropic; it's actually also inhomogeneous. So the x component, for example, has a modulation. And therefore, this component will also be modulated. And if you actually average over it, you get only 1/2 of the average, because it will have the sinusoidal modulation. So that means you can actually not calculate, must not calculate the average of this in the z direction. You actually must project it against the actual component of the magnetic field. And that's being done. And it's becoming non-trivial because it turns out that this magnetic field, even though it may have a certain Bragg-Trombi structure in the beginning, this Bragg-Trombi structure can actually evolve, it can drift in time, and so you need to calculate the phase. You can imagine this causes a little bit of MPI headache, of course, which was one of the reasons why it was in the beginning not working, and then once I fixed it, it was working, and then I forgot to turn certain switches, and I did it all wrong again. So I had to burn a lot of computing time before it was actually right in the end. Yeah. So now it's actually all good. And here are then the results. So if the lambda is the important thing. It's basically always 0. And if it's not 0, it's 0 within error bars. One exception is run A, but that's for a magnetic resonance of 2, which is just too small. The dynamo is actually decaying, and so this growth rate is negative. You also see that alpha 2, or minus alpha 2, is always positive. So the 2 alpha itself, which is here actually the sum of alpha 1 and alpha 2, and alpha 2 have opposite sign. Was that a question? So, and eta 2, by the way, is very small. The other important thing is, now for the first time we have an accurate measure of the turbulent diffusion as a function of Reynolds number. The turbulent diffusion is the blue line. It starts off with a certain value here, and it is being quenched as the magnetic Reynolds number goes up by a factor of approximately 5. If it was catastrophically quenched, which was one of the worries since 1991, it would be quenched in proportion to the magnetic Reynolds number, so that must then go down linearly, and this is still not the case. So this would be the slope in which it would go down. If it was linearly, it's still much shallower, and is perhaps even leveling off. So that was very important to demonstrate for the very first time that the turbulent diffusion is not catastrophically quenched.
But how do you define it? I want to be sure that you reach a saturation state for corresponding to lambda equation.
Yeah, yes. And it takes a long time, of course, and we have to do it by, with large Reynolds numbers, you cannot actually wait that long. You have to do it by remeshing and then evolving. So you bring it very close to the saturated state, and then you evolve it, and then again you have to wait for some time, quite some time. So that
your error bars are computed using...
Yeah, the error bars, so if you have a time series, and it would not be correct, as you would naively think, to calculate error bars based on the RMS values of the fluctuations. So it's an important thing, I think, there's a good pen, yeah. For everybody who's doing any type of data analysis in terms of time series, so if you have the time series of your data, so let's have this being the zero axis, and then the fluctuations about are like this here, right? So what you could first of all do is you take the average, which would lie here, and then you calculate the RMS value of the fluctuations about this average, and that will always lie like here, in this range. And that's, however, not the error bar. It's only the variance of the signal. The error bar means how accurate is actually the determination of this average value. And the procedure that we use is to take the following. We take the full time series over which it looks approximately stationary, which is from here to here, calculate the average, we have the average. In order to calculate then the error bar, we split this into 3 equally long bits. We take this time series from here to here and calculate average. The average may lie here, approximately. Based on this next strip from here to here, the average lies here, and here maybe the average lies here. So we have 3 different determinations of the average now, and based on this, we can estimate what the maximum departure from the actual average, and we take this as our error of the calculation.
But with only 3 integrals, you can easily estimate how many realizations you need to be completely off with that.
Yeah, so if the time series is far too short, of course, this will be completely useless, yes. But if the time series becomes long, you can get a reasonable estimate, and you can also take even shorter intervals.
No, but just by statistical fluctuations, you may happen to have the 3 being closer to the average, and you will every now and then run into that just by accident.
Yeah, but no, that also no. I mean, that takes the maximum departure. So
you will not have only up to 3.
You will not have every. Okay, I see. You think that every 3 are very far away in the average, but then why should they be so close to 0, and yet the average is inaccurate? I mean, I would then regard this as an accurate determination of the average. If 3 different independent intervals gives the same value.
But for a few realizations, you will probably be right, but it's a probabilistic thing. So if you do enough experiments, you are almost certainly going to run into a case where you roughly misestimate the standard deviation just because in one case out of that many this will happen.
Yeah. Okay, yes, so in other words, you're basically saying there's an error to the error bar, of course, and that I would accept. We sometimes don't know this. What we happen to have is sometimes very small error bars, which don't need to be accurate, of course.
In most cases, the variance, if you figure out how to get from the variance to this error, to the standard deviation,
then you don't.
More reliable.
But you don't.
But you
There's no connection. The variance can be very large, and you do a longer time series, and becomes largest, and it's of course unchanged, the variance.
You have to divide this by something like the square root of the number of correlation times or something.
Of correlation times, yes, but then you have to know the correlation times, of course. Yeah, okay, yeah, we could maybe compare these 2 different estimates, yeah, okay. Good, okay, finally, One more thing about it. So what we find this quenching by a factor of 5. But this is actually something which is consistent with an earlier result by this Tarek Youssef, where we calculated the turbulent diffusion basically just by taking a sinusoidal signal and letting it decay with time. Based on the exponential decay, we can calculate this for different field strengths, and we found this type of physics formula. And again, if you apply this with this ratio, which is approximately 2, and this empirical factor of 3, you find a maximum quenching by a factor of 6. So again, consistent with what we have found here. And you would not expect more than that. And then, now why is the tensorial structure possibly so important? So here's one application. If you were to ask, how would any other passive vector field evolve? And that's what we discussed over lunch here. Any passive vector field which follows an induction equation, but it's not actually the induction equation that is affecting the velocity field, but it's a separate induction equation, a passive vector equation. Would that, for a saturated dynamo, constitute a growing or a not growing solution? And of course, that was a question that Fausto Caranillo asked some weeks ago in the conference in Santa Barbara, and we were immediately discussing it over lunch. And you can, of course, answer the question by using our test field method, but turning off a few components here. So we have to turn off the subtraction of the EMF and the inhomogeneous term. So that's, if you do this, and that can be done by certain switches in the pencil code, you are actually solving the induction equation for a second time, and even a third time. We do it with a different initial condition, and we see that if the dynamo saturates, here's the RMS magnetic field of the dynamo, this passive vector equation, which is called B tilde, initially also grows because everything is linear, but then it begins to saturate because it was close enough to this field, but then it finds later on another solution which is more optimal, and this different solution continues to grow. And this can be...
So Andreas Tiltner and I guess right.
What?
Andreas Tiltner and I guess right.
Yes, so you were on the table with us. I forgot your name. Yes. Because I have been, yes, I was...
I joined you halfway through this.
What?
I joined you halfway through the lunch.
Yes, exactly. That was great, wasn't it? So then we had this guess. And what was your guess back then?
I think me and Andreas were the two people who thought it would continue to grow.
Yes, but I also thought it, no?
I don't remember.
But it was positive.
I think you wanted to see the...
So now we have, so now Andreas and I actually wrote up something on this. So what happens is this can actually grow, but you can even, so potentially you would think this is devastating news for the test field method, because all of a sudden we find that something which looks a bit like a test field behaves so completely different from the actual magnetic field. And therefore, in an earlier paper of May the 9th, there's a paper by Caranillo and Hughes where they say that the test field method can only work correctly if we take test fields that are close to the actual magnetic field, which is clearly not the case in our calculation. So therefore, implicitly, of course, this constitutes the criticism of our method. But the result that we obtained with our method, namely this tensorial structure and the signs which are opposite, we can now actually use to understand this result. So now let's look, how can you possibly evade quenching of alpha? So alpha consists of these two terms. The two have, however, opposite sign, and they do also have opposite sign in the case of the Roberts flow. Of course, they are being quenched, because if you adopt this with the magnetic field, this guy here, it becomes equal to B. So in other words, this becomes alpha 1 times Bi, and this becomes alpha 2 times Bi times Bj times Bj divided by B squared gives 1. And so again it's Bi. So it's the sum of the two, but the two have the opposite signs, so they quench. But that's if you dot it with the actual magnetic field. If you dot it with the B tilde, like here, you can actually completely escape any quenching if this B tilde, your new vector field, happens to be out of the null space of this matrix. So then all of a sudden you have a different vector field, which of course you cannot have if this is the same one. But if you have a different vector field, any multiplication with this vector field can lead to 0 if this new vector field is out of the null space of this matrix. And that's exactly the solution to the problem, and that solution looks a bit like a Beltrami field. It's sine and cosine minus instead of the cosine sine. And so it's phase shifted by pi over 2. And so you can then look at this solution at different cross sections, and the two are phase shifted by exactly pi over 2.
In other words, or part of this is that it's everywhere orthogonal to the average field, right? I mean, the last one.
Yes, it's orthogonal everywhere. B tilde is orthogonal to B, you mean, yes, right. Okay, and I think that is basically it. So I think that was a good demonstration that the test field method actually is not only correct, but it actually also helps us understanding surprising results with very elementary methods. So this table discussion that we had is as easily explained as by just looking at this equation. Okay, I think I have spent enough time here.
Any more questions or comments?
So there is only one field B tilde which will grow in such a case.
Yes.
No other field will.
That's interesting and correct. There could be other ones which are growing less quickly. Because if you are just a little bit off,
Because instead of a zero eigenvalue, it has a small eigenvalue. Or
it has a small eigenvalue, yes, exactly. So it will not grow as fast, but it will grow more slowly. But if you are very close to the initial field, it will grow very, very slowly, of course. Not sure whether there could be any fields which are actually decaying. That could actually, I think that could actually also be the case. If you do a phase shift, yeah, that's interesting.
The initial field that should decay.
Yes, if you, but that requires, of course, that you have to keep it exactly in phase. So that's not possible, of course, in practice. You cannot keep a vector, an unstable vector, along an. You cannot keep a vector which is free enough to choose its phase such that it will go fastest. You can choose it to be slowest. But that's maybe an interesting demonstration. Good point. We could start it off by exactly the bad one, and then it may actually decay in the beginning and later on actually increase. That would be a cool
So
demonstration.
you may have one which has a large component in the bad one and a small component in the good one. And then one component will grow and the other will decay.
Yeah, exactly. Oh, then the full field will first perhaps also indeed decay, and then later on, very later, very much later perhaps, increase. That's not bad. Yeah, very interesting. Good, so then,
Alright.
yeah?
So I suggest that we take lunch now until say 1:30 and then break.
A second, I have a good news. So with Petri's tip, I use something called n-tot Python distribution.